multi-level inverter topologies that we are discussing. Basically, you know the use of multi-level inverter topologies to what we are going to do for high power, high voltage, means high power, high current, high voltage application, that we are going to make use of this multi-level inverter topologies. As we come across, means like the fundamental and the conventional multi-level inverter topologies are of what we said, flyback converter, cascaded H-bridge, multi-level inverter topology, then the diode clamped multi-level inverter topology. That the classification, we discussed about the classification about to this conventional multi-level inverter topology, and the employment of this multi-level inverter topologies depends on your application as well. The best suits for your application for the distributed energy sources is of a cascaded H-bridge multi-level inverter topology. And also what we said, one more thing, by employment of this cascaded H-bridge multi-level inverter topology, that we can have the modularity. Modularity means what's the modularity. Now we are going to have the talk on this one, that is the modular multi-level inverter topology. This modular multi-level inverter topologies, what does it mean? Means like we are going to have the repeatability. Okay, repeatability. If you are having the same multiple units, that we are going to make it connect it into the means like either series connection or of a parallel connection, same structure. So with by having this one, that the most popular modular converter topology means that you will say that it is of a cascaded H-bridge multi-level inverter topology. What is the advantage of having this one, that is the modular multi-level converter topology? Yes, that the means like modularity means that you can say that it is of a repetition of the same unit. Modularity means that is the repetition of the same unit. If you are going to have the repetition of the same unit, what is the advantages that you are going to obtain? Yes? Rating will increase by means anyway by adding the series connection or a parallel connection, that we are going to increase the power rating of your converter. Then other than this one? Why? Waveform quality. Yeah, anyway that we said that the waveform quality here in this one, that we want to achieve the sinusoidal waveform, that will be okay. This is the staircase by increasing the number of levels that we will get. By employing either other types of multi-level inverter topologies, such as the flyback, or of what we can say this flying capacitor, or of diode clamped multi-level inverter, that also we will get it. But more among these three types of inverter topologies, that the modularity that can be done means found more in this cascaded H-bridge multi-level inverter topology. So here what is this one? Means like here also we can get it. Okay, that the module means like in modularity, which one means that the preferred one is of cascaded H-bridge multi-level inverter topology. Yes, that one means like number of levels, power rating, means like power handling capability is going to increase. Okay, anyway, other than this one, I mean to say that the flexibility of usage of this multi-level inverter topologies, we are saying that repeatability and the redundancy. Yes, repeatability and the redundancy, that the same structure that we are going to repeat. So there won't be much additional effort in terms of the switching pattern, in terms of the the structure development is going to be of more same. Okay, so that if there is any kind of faulty model which is present in the system, that we can so easily replace that model, and we will run the system. That is one advantage. And also when it comes to the switching pattern is going to be of same, and means like the structure is going to be of same, then the design of your heat sinks, gate driver circuits, all are going to be of more or less same. Okay. So this is what that the advantage that we will get it. So by using the modular multi-level converter. So that the modular multi-level converters or of inverter modules are made up of, that is the basic keys of off-bridge module or of a full bridge module. This is what. And here can't we get the modularity in this flying capacitor or of neutral point voltage clamping inverters? Modular can be modularity in the sense that repetition, I mean to say that a repetition of the converter module for your applications. So, can't we get in this case flying capacitors or of neutral point voltage multi-level inverters? Can we get? Yes? Huh? No. Yeah, no or yes. If yes, what is the reason? If no, why not? Huh? Not? Yeah. 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 Switches will be increased, but here also, but you see that in the case of what we can say that that is the two-level inverter topology, that if you go for the two-level inverter topology, if you apply the SPPWM technique, that you are going to have the 8 switching state. Similarly, if you SPPWM technique, that if you apply for a 3-level diode clamped or of a flying capacitor multi-level inverter topology, how many switching states are going to be there? How many switching states are going to be there? No, that is the 3-level. 3-level diode clamped multi-level inverter. Yeah, yeah, that is the number of level that you will get the 21 switching states, and 24 of active states, and you have the small voltages, medium voltages, and the large voltage vectors are going to present. And this one, it is of somewhat that my intention that the 3-level diode clamped multi-level inverter itself it is a complex. Then if you go for the higher number of level, that the switching pattern is going to be of much more complex. It is not of repetition. That is the reason it can be done modularity, but at lower level, not at the higher level. Up to means like that the popularity 3, 4, 5 level. For your academic means academic also, that you can have the 3, 4, 5 levels, that you can get it in this one. And also one more thing, in the case of cascaded H-bridge multi-level inverter topology, that you can't obtain the even levels, you will get the odd number of levels. Okay, whereas in this cases that you are going to get the even level of output voltage also. Okay, this is what we can say that is the majorly, that is the repeatability and the redundancy is a major factor. So, it makes more feasible to develop the modular multi-level inverters by using the cascaded H-bridge multi-level inverter topology. Yes. So, that is what we have seen in our last class also, we have come across all these things, okay, and yeah, this thing. Now, yeah, this is something that we said, we discussed about all the things about this one. You know that the output of one converter is given, I mean like that the output voltage here, which is V output, which is equal to, what is the output voltage expression? V1 plus V2, okay, V output which is equal to V1 plus V2, that we are cascading, means like adding together to get the resultant output voltage, that will be equal to the V1 plus V2. That the similarly that the waveforms also which we have shown, okay, V1, V2 and the number of levels, it is for the 5 level. And also one more thing that we have said, that the interesting thing is that VDC and this one is of VDC 1 and this one is of VDC 2. Okay. This classification is of two types of cascaded H-bridge multi-level inverter. One, what we can say that it is of a symmetrical configuration and the asymmetrical configuration. What is symmetrical configuration means? two voltage sources supposed to be of equal in magnitude. Okay. If it is of different in magnitude, we can say that it is of asymmetrical cascaded H-bridge multi-level inverter topology. If the DC sources are of different, then we are going to lose the modularity. Yes, that is one more disadvantage also what we can say, that if the DC sources are not going to be equal, then the switch ratings, okay, switching pattern is going to be, means like that the switch ratings are going to be of different. So, that we are going to lose the modularity. If it is of symmetrical in nature, then the modularity that can be obtained. Okay, that should be careful that this should be of symmetrical in nature, then only that the modularity concept that can be applied for getting the required voltage levels. Okay. That is also you think that this is supposed to be VDC1 and VDC2. Most of the applications what we are going to see that VDC1 equal to VDC2. If it is VDC1 is not equal to, I mean to say that if it that the two sources which are not equal in magnitude, if you take that the VDC1 output, what we are saying is that VDC1 V output equal to VDC1 plus VDC2. If VDC1 equal to VDC2, then we can say that it is of a symmetrical configuration. If it is VDC1 is not equal to, okay, VDC2, it becomes the asymmetrical. And then what we can say that the modularity that it is going to be obtained by using symmetrical configuration. Modularity is going to be achieved, that is the modular multi-level converter that can be achieved by using the symmetrical configuration. This is advantageous in terms of the similarity. What we can say that the gate circuits are going to be similar, okay. Power circuit means these power circuits are of similar, and also gate circuit, power circuits and the heat sink design is similar, means like are going to be of same, I mean to say that. Okay. These are the something, means repetition that can be meant for the high power applications. High power application that can be employed, this kind of configuration. So, this will be okay, that is for 2 level. If it is of a, means like this V output, I mean to say that it is V01, V02, sorry, V01 plus V02. So, for if you wants to go for the more number of levels, what we are going to do, that one more stage that can be cascaded for this existing one, another one, that the output that will be given as to the input to the next, then the equivalent voltage, it is going to become the V output, which is equal to V01, V02 plus V03. That is what we are going to see that. That is the symmetrical and the asymmetrical configuration. This is we have seen, and also that the output voltage application of this one Fourier series means for evaluating the total harmonic distortion, these things that we are going to have the analysis. We have seen, and also this one what we can say that it is of a 7 level, that we are having the 3 different equal DC sources we got, but this switching pattern is not for this one, for some other thing. So, now this is about the means modularity that we are discussing, more popular, that is the what we can say that is the cascaded H-bridge multi-level inverter topologies are more popular, I mean to say that. And also here this diode clamped multi-level inverters and the flying capacitor multi-level inverters are going to make use of a single DC source, whereas it is going to make use of the multiple DC sources that we are making use. So, consist of a series of H bridges. The function is to synthesize the several separate DC sources. Does not require any clamping or a flying capacitor. It does not require any type of clamping or of a flying capacitor. Without making use of any transformer, that we are going to increase the voltages. Okay? Without, that is the advantage of the multi-level inverter topology. Without that, the making use of the transformer, that we are going to increase the output voltage. Okay? Here, is there any transformer component is present? No transformer component. So, without using that we are going to increase the output. Well suited for the renewable energy sources, least number of components, easy to implement since each H bridge has the same structure. This is what we will say that. Yeah, fine. Now, we will go to the this modular multi-level converter topology. This modular multi-level converter topology, what we can say that each submodule, these are of submodules which are connected in means like series cascade form to get the means like required output voltage. These submodules each are means like it is made either off bridge or of a full bridge configuration. Okay? That to increase the more number of level, that we are going to make this all the submodules SM1, SM2 and SM3 up to SMN, which are of submodule. It is what we can say that the first leg is associated for the one phase, the first phase, phase A, phase B and phase C. Okay? 3 phase. Whatever that we have seen, it is for the single phase system. Like this one, if you are having the 2 more phases, it will be means like connected in parallel with a phase difference of 120 degrees, it becomes a 3 phase system. So, here for a 3 phase system, that we have this kind of submodules to increase the more number of voltage levels to means reach to the required output voltage and the output current. And also this one you are talking about mostly that the what DC link capacitors here, that the 2 DC link capacitor, that the emergence of your common voltage and neutral point voltage equal balancing, that can be associated here. Okay? VDC by 2 VDC. What are this one? That we are said it is a what is this one? VDC by 2, VDC by 2, how these are the virtual DC link capacitor. This DC link capacitors are of equal in magnitude, that is C1 equal to C2, this one C1 equal to C2 virtual voltages, these are of virtual voltages, I mean to say that C1 equal to the C2. This will be you know all the time when you are working with this kind of flying, it can be these submodules, what we are saying that we are having this off bridge inverter or of a full bridge inverter module cascaded, this will be. And then here this thing we are saying that VDC by 2 C1 and C2, that the common mode voltage and the voltage balancing, that the capacitor means this should be of equal in magnitude. If it is not equal in magnitude, that we are saying that output is not going to be of means sinusoidal in nature, it is of a what we can say that some distorted output you will get it, that the distorted output is going to ruin your machine performance in the terms of the pulsating torque and the heat generation in the machine's part, that it is going to ruin the means like machine performance, that the performance is going to be degraded, that we have to take care of the concept what we are saying that neutral point voltage diode flying capacitor multi-level inverter topology, this they will work more on this one. So, it offers what we are saying that it is going to offer an optimum trade-off between the output quality, reliability and the efficiency. Okay? It offers optimum trade-off between output quality, reliability and the efficiency. You know that output quality, reliable and more efficient, making an assumption that the power conversion is going to be of ideal cases, that is the 100% efficiency. High scalability. High scalability means that is the repeatable. It has low filter requirement. We are not making you, when you are going for this kind of cascaded H-bridge multi-level inverter topology, we are not going to make use of any kind of what we can say that the filter. Okay. And then scalability, low filter requirements. In addition, it does not require any input transformer. Okay. That we are. So, one thing that we are saying, that the AC, that we are doing the conversion from the DC to AC part, okay, DC to AC part. Some applications will accept, even if you have the positive voltage and the negative voltage, it can be acceptable, but it is not of a good, and it is going to associate with the more number of what we can say, that is the harmonics. How I can develop any type of inverter module. How you are going to ensure that my inverter, means like you said that one parameter, that is the THD calculation. If the THD, if you are going to maintain with less than 10%, that you will say that your converter is okay, means like your inverter module is working perfectly, that can be applied to your what the application part. But THD is the only parameter that we have to take into the consideration. Yeah, think. What? Okay, is that the less number of what we can say, that less number of switches, that is the means like structure towards the structure to get the more number of levels. That is one thing. That we will discuss a set of parameters which are floated, means like whether the developed converter inverter module, multi-level inverter is going to work properly or not. Not only this one, in terms of the 1 THD, distortion factors and the form factor, all the things, if those things are there, that we will discuss. So, now this is one a modular converter. This can be meant for the high power, high voltage applications. Okay. This we can say all these are of submodules, that you can imagine that now that the laboratory experimentation is going to be of more what we can say, that it is of a complex, that the big diagrams will be there, and also you want to realize the laboratory form, it will be of some specific applications and the industrial sponsored things only, that we can have the means like prototype things. We do have certain modules also of 2-level, 3-level inverter modules are there. We will have the cascading, and they will go for the experimentation. Then next, this will be MMC. In short, we are representing that is the modular multi-level converter is of MMC. You see that each cell, either it can be off bridge or of a full bridge, it can be cell 2, cell 3, cell 4, like this one. It can be made employed to up to means like 3.3 kilowatts to 13.8 kilowatt. This cascaded H-bridge module is a subset of modular multi-level converter. It is a subset of the bigger one, that is the modular multi-level converter. Cells can be made up of half bridge or full bridge circuit, controllable voltage sources. Controllable voltage sources can be manipulated. Okay. Controllable voltage sources, output voltage that you are going to, and these are of unequal in nature. What it is going to be, that the modularity that can be lost, that the modularity means like that the again that I am stressing, modularity means it is a kind of a repeatability and the redundancy part. This is what we can see that in the case of what we can say modular multi-level converter topology. This is the diagram which I have taken from the reference. Yes. some of the applications where we are going to apply. Most of you that you are working about what we can say that electric vehicles or something, and electric vehicles power factor correction, those things. But here that this can be made for the high power applications such as HVDC transmission, STATCOMs, motor drives, wind energy system, PV system, traction power supplies or of traction drives. I mean to say that it can be employed in chemical, oil, liquefied, natural gas plants, water plants, marine propulsion, power generation and the energy transmission application. These are going to made use, okay, for this. You know, at the time of generation, distribution side, that doing the conversion from AC to DC and DC to AC, that these types of multi-level inverter topologies are going to play the crucial role, okay. There at the time of transmission, distribution, generation side and the distribution side, these are more popular, I mean to say that. Yes, fine. So, up to now I mean to say that we have come across the basic conventional multi-level inverter topologies. So, there are what we mean to say that there are the two ways to work in the case of multi-level inverter topologies. One is in terms of developing the structure part, and the another one is of a modulation strategy, okay, modulation strategy. With the minimum number of switches that you can get the more number of levels. With the with minimum number of switches that you can obtain the more number of levels. That is the one objective of your developing the different structure. And modulation with minimum switching pattern, that you are required to obtain the what pure sinusoidal waveform, okay, as close as possible to the sinusoidal waveform that we are supposed to obtain. This is what we can. Now, we will discuss, we will make a move to the next part of the topic. Yeah. So, that what we are saying that the classification of high power inverter, that can be of direct conversion or of indirect conversion, which is going to make use of the DC link capacitor, okay, and it can be of matrix converter or of cyclo converter, that we can say that. And then it can be again classified into the two types. One, what we can say that whatever that we are discussing is about the what type of voltage source inverter modules, okay, not the current source. Current source inverter module, pulse width modulation, current source inverter, load commutated inverter, that we are not touching, okay. And then this voltage source inverter modules, multi-level inverter, two-level voltage source inverter, means conventional one that you are having, this conventional thing that we said, either you will get the two state, either 0 state or of a plus VDC state, or means this is only two state, that when the switch is in on condition, what we can maximum current flows, and the off condition, that the voltage across the switch is going to be equal to the source voltage. Whereas this multi-level inverter, we are having that the classification is done by making use of the usage of the DC source. Either you may make use of a single DC source, or you can make use of a multiple DC source. Multiple DC source are best suited for the cascaded H-bridge inverter module. Again this one, this structure is of more popular, cascaded H-bridge multi-level inverter is of more popular, and it can be clubbed with the other type of conventional multi-level inverter topology, that can be clubbed with the neutral point clamped multi-level inverter plus cascaded H-bridge, and the diode clamped multi-level inverter with the cascaded H-bridge. Others means flying capacitor multi-level inverter with the cascaded H-bridge. Also that can be done with the usage of multiple DC sources that we have. And again, that the classification we are saying that it is a summary what we have said, equal DC sources and the unequal DC sources. If it is of equal DC sources, what we are saying that it is of a symmetrical configuration. If the DC sources are of unequal in magnitude, we will say that it is of a asymmetrical configuration. This is more popular with the for modular multi-level inverter topology, this one. This is what we can say that the classification, you know that voltage source inverter and the current source inverter. How we can make a current source inverter? What's the means like that the voltage source inverter and the current source inverter? Yeah, if yeah, and a large inductive component which is placed in series with the voltage source, it becomes a current source inverter. And if you want to make the voltage source inverter, large capacitance which is connected across the voltage source, parallel to the means across to the source, that will become the, but this one is of more popular, voltage source inverters are of more popular as compared with the current source inverter, because you know, if you are going to make use of an inductive component in series with the system, that the response of your system is going to be of slow. That is, output voltage also becomes what we can, becomes less, that the losses associated with the inductive component. This is what we can say that. So, now when it comes to the usage of a single DC source, that we are going to employ a single DC source. If you use the single DC source, what are the different types of multi-level converter topologies that we are having? One is the neutral point clamped. This one we can say that 3-level diode clamped multi-level inverter, also call it as neutral point clamped multi-level inverter. Active neutral point clamped multi-level inverter. This is the flying capacitor multi-level inverter topologies are going to make use of a single DC source. Modular cascaded, this one also that we are saying that modularity can be achieved with this flying capacitor and the diode clamp, but at lower levels. Completely we can't say that we can't achieve the modularity. It can be achieved at the lower level, either 3, 4 or 5, because it is a well proven structure, and it will be easy to incorporate. Yes, here that single delta bridge cells, single star bridge cells, double star bridge chopper cells and double star bridge cells, that is the modular cascaded inverter topology that can be done. So, one more thing, that the input, this one is of indirect and the direct. If the source, what we are saying that it can be like you know that the conversion, usually that the input to it, your inverter module is from the direct DC source or of AC source. Your input to DC inverter module is a direct DC source or of a AC source. Yeah, if it is available DC, that will be no problem. Okay. If it is not available, what you are going to do, rectification, and the output of the rectifier will be given as a input to your inverter module. If you do the rectification, can you able to obtain the pure DC by using the rectification? Yeah, yeah. A pulsating DC or of a raw DC that you are going to obtain. So, here you want to make your output waveform as smooth as possible. Okay, that the output what you obtain from the rectifier. Yeah, I will go. That the output is going to be it will be like this. Your output is going to be like this. Okay. So, is it pure DC, that the rectifier output is going to be somewhat this one? You have suppose that, I mean to say that that the 3-phase rectifier or of a 6-pulse rectifier. 6 pulse rectifier. What's the output frequency of your 6 pulse rectifier? 6 pulse rectifier out of the input frequency. Excuse. 6 pulse rectifier, that your output frequency is going to be 300 Hz, that is equal to 50 into 6. Here in the case of 6 pulse, okay. Now if you make use of the 12 pulse rectifier, okay, how many? What is the frequency of this one? Yes, 600 Hz, that you are. And then 18 pulse, okay, 50 into 18, how much? 900, or maximum that we can go for means like 24 pulse rectifiers are there. That will be 50 into 24, you will get how much? 1200 Hz. Yeah, fine. So in the case of this kind of high power application, that we are going to make use of means like either 18 pulse or of 24 pulse rectifier. Even then also, that the output here, if you take the 6 pulse, that it will be more like this, and then here in this case more number of pulse will be there, and then here still smaller, and when it comes to 24 pulse it will be still, but you can't get the means like pure DC, that you can't get it. You will smooth it, but again to smooth for this kind of harmonics means like the ripples, what we are going to do? Yeah, that is the de-sealing capacitor we will make use. It provides the that if after means incorporating the filter, that you will get that the pure means a straight line, that you will get that the magnitude above the 0 level. This is what you are going to make it. So this is what you are going to see, that means like usually for our practical application, that the input is going to be the rectified output. Okay, rectified output will be given as the input to your inverter module. That the frequency that we are supposed to maintain. This we can see that. To the extent possible, that our analysis is for the voltage source inverter, that considering that it is of a pure DC, so that the analysis becomes more simpler. If you are having this stage, one inverter stage and the application stage, that becomes that the circuit is going to be more complex. Now if you see that whether now your inverter is working properly, now you see that what are the parameters that you are going to see, that overall contribution, whether the inverter is working properly or not. These are the means I don't go depth about the things, just to float the information I did. Traditional multi-level inverter topology, we are having the diode clamp, then flying capacitor multi-level, cascaded edge bridge multi-level, and it can be reduced switch multi-level inverter, symmetric, asymmetric, and the hybrid combination as well. Okay, it can be made use of both symmetric as well as asymmetric and forms the hybrid, and it may make use of with H bridge or of without H bridge also, configuration with H bridge and the without H bridge. This is the one part, I mean to say that it is the structured development part. When it comes to the modulation strategy, that you have to modulate or provide the switching pattern to your system part. For that the switching pattern is going to be dependent on usage of your switching frequency, either switching frequency is higher or lower. Then various types of modulation strategies do exist, that is calculation of the switching angle, neutral voltage control, selective harmonic elimination, and the high switching frequency that you are discussing about this one. What that is the pulse width modulation technology, space vector PWM technique. These are the modulation technique, basically that the classification depending on either usage of your switching frequency, either it can be of low switching frequency or of higher switching frequency. So, if you have the switching frequency higher or lower, what matters? What matters? Higher or lower? Yes, losses. Yes, that if you are going to make use of the switching frequency higher, then the losses are going to be of higher, and if switching frequency is lower, that the losses are going to be of lower. So, how this loss is going to be calculated? There is a transition. Switching loss means that the switching loss. You mean to say that the transition from the off state to the on state or from the on state to the off state. Yes, initially if it is in off state, that the voltage is of what we can say that off state means that the voltage which is equal to the source voltage, and if it is of on state means that the voltage will become now it is in off state. Now we want to bring it to the change the switching state to a on state. Then what we can say that it becomes here in this case that the V equal to VDC. Here in this case that I equal to I maximum. There is a transition, maximum current supposed to, and this thing, and again from on state to the off state. Yes, on state to the off state. Now here it is in on state I equal to I maximum. Then we are bringing it to the off state. This transition, okay, this transition from here on state, now I am bringing it to the off state, okay. Here V equal to VDC. What is the switching loss means? This is the period, okay, we will say that it is of a power loss, okay. This transition from the on state to the off state, that we will say that P loss, okay. V maximum, I maximum, it is not rated, but you know this portion. If this period is of more, then the loss is going to be of more, okay. That you can imagine that is the loss which is going to be of more. So, this thing will be there depending on your lower switching frequency or of higher switching frequency. We have the pulse width modulation and the space vector PWM technique. Then when it comes to the performance parameter, one factor that we are saying that THD, distortion factor, crest factor, form factor, means RMS value of the output, lower order harmonics, high frequency, then peak inverse voltage, power factor, weighted THD, blocking voltage, standing voltage and the power loss. These are the some parameters that you are going to completely take into the consideration while developing your new modular multi-level inverter topology, okay. THD, distortion factor, crest factor, form factor, RMS value of the output, lower order harmonics, high frequency, peak inverse voltage, power factor, weighted THD, blocking voltage, standing voltage and the power loss. Few factors means like that you are going to take into the consideration. And the next, that the control techniques depends on your, means these are the applications, I mean to say that instead of control, that is the flexible AC transmission system, motor drives and the renewable energy system, distributed energy sources, I mean to say that for this one, okay. Yeah, this is the overall contribution of your things. Now the structure, that the classification of high power inverters and means that to know the better inverter topology, that we are going to have all these kind of parameters. Yes. Now if you see that the another one, we have to go for the development of the switching strategy. In switching strategy, what are the parameters that you are going to take into the consideration? that the transition supposed to taking from the on state to the off state or from the off state to the on state. This losses supposed to be have the minimum that the losses supposed to be of minimum. For that a smooth transition should take place. Okay? Smooth transition that to synthesize our objective of making use of the multi-level inverter topologies to synthesize the sinusoidal waveform at the output level. To synthesize a sinusoidal waveform at the output, switching strategy needs to be defined. What are the switches should? You know, for a standard H-bridge structure that the diagonal switching operation is going to take place. If diagonal switching is going to take place, that you will get the plus VDC, and the another diagonal switching pattern turning on, you will get the minus VDC. Switching strategy needs to be defined. Every voltage is applied at the output with a certain electrical angle. With certain electrical angle, careful application of the angle gives lower harmonic distortion and the required amplitude at the output. Okay? Careful application of the angle, switching angle, gives the lower harmonic distortion and the required amplitude at the output. More than one switching strategies, obviously that the most of the researchers are working on this kind of switching strategy to get the required output voltages. More than one switching strategy are available for a single voltage level. Yes, this is what we can say that that is the redundancy, that is the beauty of your for one switching, you even in your what that the space vector pulse width modulation, how many zero for getting the zero output, how many switching states are there? Two switching states. One is either any combination that you apply, that you will get the zero output, that is the flexibility. Either upper layer switches, all the upper layer switches are turning on, you will get the zero output, or the lower level switches, that you will get the same but the output, that is the redundancy, we mean to say that. So, for every change in the state, only one switch shift to be allowed. For every change in the switching state, only one switch shift should be allowed. Capacitor, this is important in the case of diode clamped multi-level inverter, capacitor voltage balance should be maintained. Otherwise, common mode voltage and the neutral point voltage unbalancing is to takes place. All the switching devices should be used equally. Okay? The usage of the switching devices should be, so that what will happen, that the burden on the other switches is going to be of lowered. This is what we can see that in the while selecting the switching pattern, that these are the factors that we are going to take into the consideration. Yeah, next, if you see that the modulation techniques, we have the main aim of the modulation strategy of multi-level inverter is to synthesize the output voltage as close as possible to the sinusoidal waveform. It is possible to control the output voltage as well as its harmonic content by using the appropriate modulation technique. This is what we are saying. Many possible PWM technique, for example, means that the fundamental, based on the fundamental switching frequency, we have the space vector control, and then this selective harmonic elimination, and for higher switching frequency, we are going to employ the carrier based PWM technique and the space vector modulation. Okay. This is what we are going to have. Then, if you more focus, what I am going to do, this will be of somewhat good, easy for understanding, that we are going to make use of the carrier based PWM techniques. Okay. What is the if you want to generate a pulse to your inverter module, what you require, what are the signals you require? If you want to generate a pulse or of a PWM signal to your switch, power semiconductor switch, what are the signals are required? Yes? Yeah. One is the reference waveform and the other one is of a carrier waveform. This the For multi-level inverters, these two, that you can see that that the carrier waveform is of high switching frequency and the reference waveform is equal to your fundamental voltage level, that the 50 hertz compared with the 1000 hertz carrier frequency, that the switching pattern will be generated, that can be given to your inverter modules. Okay. Yeah, fine. So, now the question is that here for the multi-level inverter, if it is of a two-level inverter topology, is the generation of the switching pulse is of similar, but when it comes to the multi-level inverter, so you are going to make use of the number of carrier signals, and then only one reference signal is going to be there. For your multi-level inverter, if it is of a two-level inverter topology, that will be well and good. You will make one carrier signal and one reference signal, making a comparison, that the output will be given as a switching pulse to your inverter module. But when it comes to the multi-level inverter, there are series of inverter modules are going to be there, which are cascaded in form. How we are going to give the switching pulse to the, suppose that only first converter supposed to operate and the second converter supposed to operate, how we are going to make the pattern? For example, if you take the this 3-level cascaded H-bridge multi-level inverter topology, how many carrier signals are going to be 7-level cascaded H-bridge multi-level inverter topology, 7-level cascaded H-bridge multi-level, how many carrier signals are required? 3 are required. How many? You see that carrier signals are nothing but these are triangular carrier signals that we are making use. Here the 6 carrier signals are going to be required, but only one reference signal, that the reference signal is going to spread over the all the carrier signals. Okay. Depending on the amplitude of your carrier signal, that the switching pattern is going to be generated, that the depending on the switching pattern, that the things are going to be generated. In this modulation technique, carrier based PWM technique, modulation technique, sinusoidal reference signal is compared to the multiple triangular carrier signals. Okay. Multiple triangular carrier signals to produce the gating signal. It requires m-1 triangular carrier signals. The output will follow the shape and frequency of the reference signal. Reference signal frequency is going to be 50 Hz and the carrier signal frequency, it is equal to the circuit frequency, circuit operating frequency, that can be of 1 kilohertz or of 5 kilohertz of operation. THD can be improved by adjustment of the carrier signal. Okay. The adjustment may be, okay, again this the carrier based PWM technique, that we have the two types, one is of level shifting and the other one is of a phase shifting. Okay. Level shifting and the phase shifting, each thing that can be level above, one above, and then phase shifting, shifting of the phases of your carrier signals. Okay. The carrier signal amplitude supposed to be of same, okay, and the amplitude supposed to be of same and the period supposed to be of same. Okay. This should be taken into the consideration. And then we have the two classification, level shifting and the phase shifting. Okay. Again this level shifting is 3 more types are there for level shifting PWM technique, that I will discuss, and the phase shifting will be for the time being I am the time I am going to skip this one. That modulation techniques, both amplitude and the frequency can be controlled. Okay. Both the amplitude and the frequency is going to be controlled. So, if you see that carrier based PWM technique, that we are having the 3 different types: in phase opposition, in phase deposition, alternate phase opposition deposition. Okay. These are the different modulation techniques that we are having. One, all carrier signals will have the same phase and level shifted. In phase opposition deposition, all carriers are level shifted and all carriers above 0, and all other carrier signals have the different phases which are of 180 degrees phase shift. Okay. That I will show the patterns also for this one: phase opposition deposition, phase opposition deposition, alternate phase opposition deposition. Every carrier signal level shifted and are 180 degrees phase shifted with the neighboring carrier signal. This is what will have the means like these are the different types of carrier waves, that to level shifted PWM technique that we are having. So, what is the objective of going for different types of switching strategies? Once again, objective of going for the different switching strategies. We can use one PWM technique na, instead of having, why we are discussing so many PWM technique. Yeah. Yes. Yes. To 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 synthesize the output voltage, that is one thing, with less number of harmonic content, okay, lower THD value. Here also that I can see that this one is done by the simulation and experimentation. The objective based on one reference parameter, that is the THD value. Whichever type of switching strategy gives the minimum THD, that will be taken into the consideration. Yes. Yes, fine. Yeah, one more thing, that is the selective harmonic elimination technique. Here only selected harmonics are going to be taken out by using the notch filter. Notch filters are nothing but zero filters. Okay, this are of comb filters will be there. They are going to eliminate those filters, means like harmonics. Some selected harmonics could be eliminated from the inverter output voltage by introducing notches at the suitable time instance in the pole voltage waveforms. The notch angles to be calculated offline using the digital computer, and the latter used for generating the switching sequence. Okay. Which are the harmonics are there, that will calculate the notching angle, then apply to your system to eliminate those harmonics. That the notch angle information for all the three phases taken together can be converted into a, what we can say, matrix of switching word for the inverter. The notch angle information for all the three phases taken together can be converted into a matrix of switching word for the inverter. This will be taken, that the algorithms are going to be developed by using Newton iteration methods or of Newton-Raphson method. That information will be given to your inverter and it calculates the notching angle, that will be applied to your inverter module, so that the specific harmonic content that can be eliminated. That we are said that the fundamental component alone will contribute towards your output voltage, and the rest of the other harmonics are of what we can say that, which are of harmonic kind of a disturbances, that will be what we can say kind of the disturbances, those are of not contributing factors to your output voltage. And then that the switching word information is then converted into a gate control signal for the inverter switches, that the switching word that will be converted to a gate control signal for the inverter switches. So, now this is of interesting another type of what we can say that switching strategy. Now, we have another thing, optimized selective harmonic, OSHE. In this technique, every switches will be turned on and turned off in such a way that some higher order harmonic that can be eliminated. For 7 level cascaded inverter, 5th and 7th harmonics that can be eliminated. This category of modulation technique comes under the fundamental switching frequency. Switching device turn on and off only one time per cycle. This feature reduces the switching loss and the associated EMI problems that we are experiencing. So, this is one type of switching pattern that we are having, optimized selective harmonic elimination technique. Then the other one is of a that you are means like for the many classes that you are associated with this space vector modulation. That the beauty of this one is of more flexibility for getting the switching states. That the if you go for the higher number of level, for getting the same level output, there are different switching combinations will be there, switching patterns are going to be there. So, that the redundancy can be easily achieved by using this kind of space vector PWM technique. Space vector modulation, the switching state redundancy is a common phenomena in multi-level converter. Okay, it provides great flexibility for switching pattern design, especially for the space vector modulation schemes. Why we are saying that it is of a great flexibility for the switching pattern design? Yes, flexibility. For example, that we are saying that in your 2 level you have the 8 switching states, and for getting the 0 output you have the 2 switching states. Either one can be applied. Okay, that is okay. Then what is the advantage of having 2 switching states for getting the same output? Same output. Advantage of having the more number of switching states, for the same level of output. One what we can say that, yes, one what we can say that if you have the more number of states, then the stress across the switches is going to be reduced. And we will allow, there will be, these are all of practical switches. Practical switches will take certain time to come to the 0 state. Okay, that to provide the 0 means like completely turned off, completely turned on, there will be a time delay. That the time delay will be provided. Okay, with the redundant switching state. That the complete time delay, complete turn off process or complete turn on process, it is associated with a kind of time factor. The time factor can be achieved with the redundant switching states, so that stress across the switches is going to be reduced. So, fine, during each switching time period of phase voltages, 6 discrete time instances can be identified when one of the phase voltages have the maximum positive or negative instantaneous magnitude. This is for your 2 level. 6 discrete instances, these vectors are aligned along the phase axis having the maximum instantaneous output voltage. You know that you are working on this one, I do not want to, this is the one pattern for the 2 level inverter topology that I have projected, and what the output voltage, how the switching pattern will be there, reference vector, this thing. Now I will come to this thing, that the cascaded means like 7 level cascaded H-bridge inverter module by applying the carrier based PWM technique, that too level shifted PWM technique, that I can say that. These are the switching angle, and you have this one V1, V2, V3, that the output voltage which is equal to the V1 of t plus V2 of t and V3 of t. Okay, that the number of levels for your what we can say that output voltage VDC, 2 VDC and 3 VDC. On line side we are having minus VDC, minus 2 VDC, minus 3 VDC, that you are having total 7 levels that you will obtain. So, now if you see that the simulation for a 3-phase system, that we are having the 9 different DC sources. If you go for only single phase system, that you require the only 3 DC sources, but it is meant for the 3-phase system. He has made use of 9 different DC sources, switching pattern is the simulation diagram is like this. Then the first thing that we say that in phase deposition simulation. Here in phase means all the carrier signal, it is of a 7 level cascaded H-bridge multi-level inverter that we require to have the 6 carrier signal. If you see that the 6 carrier signal above the 0 level we have first, second and third, and the below 0 that we are having 1, 2, 3, 6 carrier signals are there. It is for a 3-phase system. 3-phase system, this is equal to the output frequency, fundamental frequency, that is of 50 Hz. This reference signal spread over the entire carrier signal. Okay? Then it will make the pattern to generate the PWM signals to your inverter module. Okay? This is what we are having in phase deposition simulation, means like we are having the simulation result. Okay? This is what we are having. We will make a comparison and the required pulses that will be generated to your system. Then we calculated the phase voltages and the line voltages. That the in phase voltages that we will have the 7 levels, in the line voltages you will have the what we can say that 13 levels that you will get line VAN minus VBN, VAB which is equal to VAN minus VBN. Okay, line to line voltages and the phase voltages that we projected 0, VDC, 2 VDC and then 3 VDC. Here we have the 13 levels line to line voltages. Then other thing, phase opposition deposition. Phase opposition deposition. If you see that earlier case, all the here all the carrier signals are in phase. Okay, here all, if you see that carrier signal 1, 2, 3, all are going to be of in phase deposition. All are in phase here in this case. All are going to be in phase. But when it comes to this case, that the phase opposition deposition, if you see that the first carrier signal and the below this one is of 180 degrees phase shifted. Okay, second carrier signal and then this one is going to be a phase shifted by 180 degrees, and the third one which is phase shifted by 180 degrees. Okay, this is what we are having. Then the results for this one, that the line to line voltage and the phase voltages for the 7 level cascaded H-bridge multi-level inverter, these are the things. So now the another scheme, yes, alternate phase opposition deposition. Any phase means like any two carrier signals are not going to be in phase. If you take this one, carrier 1 and 2, they are in alternate in fashion. Okay, one it is of starting from 0 and the other one is starting from the 180 degrees. Okay, alternate phase opposition deposition. If you take this one also, 180 degrees phase shift is there for this one. So alternate phase, that the name itself it indicates the alternate phase phase opposition deposition pattern. Okay, that the reference signal is of 50 Hz, that is the fundamental one, then we will get this kind of pattern. Yes. So here for this one also I am little bit moving faster to close, and then this one we are having the phase voltages and the line voltages for the 7 level whatever. Now the objective of having this thing optimized, yeah, this is one thing, and the another one with the selection of optimized selective harmonic elimination method, that we are having this one. This is what we have done. So then afterwards, that the objective, which one is the best, that the pattern that can be done by using the FFT analysis of this output voltages. FFT we calculated the like for a fundamental frequency component, we got the THD value of in phase deposition 11% and in this case 16 point, this case 15 point, and then optimized selective harmonic elimination we got the THD value of 8.72%. So among this one, that we can say that in conclusion, that we can say that optimized selective harmonic elimination method is the best switching pattern for our cascaded H-bridge 7 level cascaded H-bridge multi-level inverter topology. Yes. So, anything you have any queries regarding for this one? These are, yeah, when it comes to this thing, that the 7 level voltages cascaded inverter is simulated using all the techniques compared with the THD value of the output voltage. This one, that is the proposed optimized selective harmonic elimination technique, has the least value of THD, is the best suitable modulation technique for the system. So, it is because reduced switching losses, easy to use for the renewable energy harvesting. Yeah. No, no, it is generic one that I projected here. Means like only for the cascaded. Our system, we have taken the simulation work for cascaded H bridge, not to the diode clamped multi-level inverter. It can be applied, but you know that you can have the calculations. This thing. Yes, it can be employed. Okay. All the switching patterns are going to be of same. It can be applied to any of the multi-level inverter topology. Yeah, MMC is more popular with the cascaded H-bridge multi-level inverter, and also it can be made with flying capacitor, diode clamped also, but not higher number of levels. Here it can be made higher number of levels, okay, by using the cascaded H-bridge multi-level inverter. Yes, fine. Any means like that the things are there. Oh, sorry, I don't want. Yeah. Anything that you can have, this one, this. Some questions? Yes, you. Anything? Questions at your side? This PPT. Yeah, I will share. Okay, I will share in WhatsApp group. It is there with me only. That okay, I will share with you in WhatsApp group. And that too, that the yes, if the things no more queries, then we'll stop the session again. Then we'll continue for the validity event.